morning, myself K. Prashant. I am PhD scholar at JNTU. Today I am going to explain real-time conversion of 2D video to 3D using embedded systems. In this topic, real-time 2D to 3D conversion for television broadcasting based on embedded systems. This is the advanced topic in embedded system. Generally, image is captured in two-dimensional, but its conversion takes place encoding and decoding steps and some processing steps. I will explain. In these, main objectives are convert live two-dimensional signal into three-dimensional video in real time and estimate the depth information from monocular video frames, generate stereoscopic left eye and right eye images, minimize processing latency for live broadcasting, support HDMI, SDI and digital television standards, improve viewer immersion system hardware, and finally the video stores in the memory. The block diagram of real-time 2D 3D conversion for television broadcasting. Real-time 2D to 3D conversion for television broadcasting based on embedded systems. Based on block diagram, we have 2D camera is an input and its camera output is HDMI or SDI. Initially, pre-processing stage is there. In the pre-processing of the video, frame capture, synchronization steps will be happening in the pre-processing. 2D to 3D conversion engine will is based on our main conversion steps. Here in this first step is depth estimation for stereo using some algorithm. This step, the depth estimation depends on the quality of the video and algorithm. View synthesis, next step. Here how much left eye view generated and how much right eye view is generated is calculated in the view synthesis. And the next step is 3D. Mainly the balance between left and right eye is calculated, and finally efficient frame rate is calculated, and all these steps are happening in the embedded system processor based on FPGA, and finally stores the data in the flash memory or DDR. And if we see the output, final output will be a 3D output, and for this we will be having the glasses, and right eye vision and left eye vision is separated by using this technique in the embedded system. In the flow chart, we can see starting step is capturing of the two-dimensional video, and next step is pre-processing, and another step is depth estimation, and the next step is view synthesis, means how much a left eye can view, how much a right eye can view, and after this 3D rendering, means after separating the left and right images of that video, we have to make it as a 3D, and after 3D optimization then only we can generate output 3D video, and this 3D video is we can view through HDMI or SDI, and after the completion of this video processing, final output is a three-dimensional video. It's a workflow. Generally a 2D camera is installed and it captures the frame. After that some depth estimation steps, and after that the view synthesis steps will be there, means left eye vision, right eye vision, and 3D processing. Finally is 3D outputs. If you see its block diagram, simplicized block diagram, we have the camera is the input, camera will capture, and pre-processing of the capture video, and depth analysis is happening through AI, and this 3D engine will take care of right eye and left eye view synthesis, and finally encoder will convert a 3D image. That image is given to the TVs. In the next step, 2D to 3D processing flowchart, as we observed, the main role is 3D engine. If we see the hardware, if we see the components of hardware what we require, generally hardware components required for these processing steps, mainly ARM Cortex processor, FPGA or DSP processor, DDR memory, HDMI SDI video input interface, HDMI video output interface, flash memory, power supply and cooling system. These are the main hardware components required to convert a 2D captured image video to 3D capturing. The main essential software components involved here are real-time embedded Linux software or real-time operating system, and OpenCV imaging processing library. This is related to AI. Depth estimation of algorithm is required. Stereo view generation algorithm is required, means how much a left eye can view, how much a right eye can view is depends on this stereo view generation algorithm. Frame synchronization module, video rendering engine. These modules are essentially software components processing. The main working principles here we can observe. First, we will capture live 2D video from broadcasting source, and we will perform some pre-processing steps to remove the noise and improve quality, and we can estimate the depth information using processing algorithms. And next, using view synthesis techniques, we will calculate left eye image view and right eye image view, and after that we will perform 3D rendering and frame optimization. Next, display and transmit generated 3D video through HDMI or SDI interfaces, and these steps are repeatedly performed to get the continuous output. The major processing stages are here 6 stages. In the first stage is video capture, in the second stage is image pre-processing, in the third stage is depth estimation. In the video capture itself, we will use one HDMI source or SDI using some camera module. In the image pre-processing stage, we are mainly focused on noise removal, so some contrast enhancement steps will be taken care, and color correction will be taken, and frame synchronization steps will be taken in the image pre-processing. In the depth estimation, generally we will go with some AI based algorithms. It calculates depth map from each video frame, uses edge detection and object segmentation or AI based estimation. In the next 3 stages, we will see view synthesis, means how much a left eye view and how much a right eye view, and next stage is 3D rendering, and next stage we can, after generating a 3D video, we can broadcast very easily. The main advantages here mainly on real-time processing. Main advantages we can use using 2D to 3D video processing. First one is real-time processing. Second one is enhanced viewing experience. No need for dual camera systems. This is the very much good feature we can expect. Mostly 3D cameras will cost more, and to capture the 3D image it is very difficult task, and we require hardware difficulty. So no need for dual camera systems. Low processing latency and compact embedded hardware, means large hardware is not required. A very simple hardware to make a 3D video capturing. Energy efficient operation and cost effective broadcasting solution, means with less cost it will support more features. Live broadcasting of sports these require some 3D imaginations. Supports existing television infrastructure. If we see its applications, it is mainly used in live sports broadcasting, and second application is entertainment channels. Third one, mostly kids will like 3D movies. In 3D movies, This application is very much used, and educational televisions for 3D images like cube structure, cuboid structure, and medical visualization, and virtual reality broadcasting, documentary production, digital signage. The main essential requirements in applications, and thank you all.